All right, so now we move on to lesson 4.4a, which is all about optimization problems. And 4.4b is going to be also on optimization problems. So beware for lots of different types of optimization problems where the idea behind extreme values is going to help us assist in finding maximum and minimum values. Now, in optimization problems, there's a lot of steps. So first of all, we want to assign some variables, aka clearly define those variables, draw a diagram if needed, write an equation to quantify the object being maximized or minimized, rewrite the equation in terms of one variable using substitution, find the derivative, reveal the critical numbers, use those critical numbers in the first derivative test to determine where the maximum and minimum values are at, and then finally use your answer to determine if there's an absolute maximum or an absolute minimum depending on that answer. Now, that's a lot of steps. So the big thing is just going to make sure to practice and then get lots of different exposure with the different methods in this note package here. Now, in example one, what they ask us to do right away is find two positive numbers who add to make 15 or sum to make 15, and the product is an ending maximum. Now, as soon as you see that keyword of maximum, you want to highlight that right away because if they're talking about a product being a maximum, then when we do our first derivative test, this should reveal a maximum. Okay, revealing some of the steps here. So right away, two positive numbers who add to make 15. We want to define the first number and then figure out the second number from there. So I'm going to say let x be the first number. And I'm just going to short form it like this. And then I'm going to say let 15 minus x be the second number. So clearly just stating what these two numbers represent in terms of how we're going to use them in the problem. Now, the product, which we're going to denote as p, the product is equal to these two numbers multiplied together, so x times 15 minus x, which will give us the other number. And then from here, I want to just distribute this so that I get the product is equal to 15x minus x squared. Now, we're going to take the first derivative. So because we want to do our first derivative test to determine a maximum minimum, we got to figure out the critical numbers. I'm going to write this as dp over dx, which could also be written as p prime of x, is equal to 15 minus 2x. Now, to find the critical numbers, we set this equal to 0. So we go, the first derivative equal to 0 is 15 minus 2x. Therefore, when we solve for x, we're going to end up getting that this becomes 15 over 2. Perfect. Now, that's our critical number. So I'm going to say in brackets that this is a critical number. You could also say critical number at this value. Okay, here's where we do our first derivative tests. We found our critical number for step number 4. I'm going to go, let's draw out our tables. So I put together a small table. I put together my one column row, and I'm going to put the 15 over 2 right on that line. On the outsides of this, I'm going to put 1 and 8. I'm going to put test point right here. And then I'm just going to write in p prime of x and p of x. So basically just saying what happens to the derivative on the left, what happens to the derivative on the right, and then solving. Now, you could write in the actual derivative itself, 15 minus 2x, but I'm just going to put that in there and do our sign analysis. So from here, p prime of x, if I sub in 1, I'm going to get a positive. If I sub in 8, I'm going to get a negative. Therefore, the function is going to be increasing on the left-hand side, decreasing on the right, and hence at this critical number, we have a maximum. So I'm just going to indicate that below and be like, yep, we get a maximum value from here. Now, we got to figure out the two numbers, right? So, because they said, what are the two numbers here that produce this maximum? Not necessarily what is the maximum, but what are the two numbers? Step number 5, if our x value is equal to this 15 over 2, then when I solve for the other value, it's going to be 15 minus x, which is equal to 15 minus this 15 over 2, which will end up giving us a value for the other number of, this becomes the 15 over 2 as well. So the two numbers that lead to a maximum product are both x equals 15 over 2. Or because we're saying the two numbers, and I don't want to confuse x representing directly both, I'm just going to say that they're both 15 over 2, period. There you go. So we have a sentence. This reflects our overall answer, and it's very clear of what we're describing this value as. Now, it said as an exact value, so I'm going to leave it as 15 over 2, but if it ever asks to like the nearest 10th or nearest 100th, you could also round that there. Okay, perfect. Let's continue forward into another type of example like this. So find the dimensions of a rectangle if the perimeter is equal to this and the area is a maximum. So right away I highlight that we're looking for a maximum. And then what is that specific, what is the specific maximum? So not only are we finding the dimensions, but we're also finding out what the overall maximum area is. So from here, what we're going to do is we're going to look at this and go, step number 1, let's define our variables. Let the length and width, aka let L and W, be the length slash width. And on top of that, I'm going to write in L and W, both must be greater than 0. Because if either one is 0, then we're going to be in trouble because we can't have a rectangular shape unless we have a length and a width, or else it'd be one dimension. Okay, now from here, we're going to go step number 2. Well, they gave us some information about the perimeter. The perimeter is equal to 28, which is equal to 2 lengths plus 2 widths. Now, the reason we're going to start with the perimeter and then move to the area from here is you always start with the equation of the information they gave you. So if the perimeter is 28 and we don't know about the area, we're going to start by using the perimeter to get this in terms of one variable. So from here, I'm going to look at this and be like, well, that means that 28, and let's say I solve this for W. That means 2W is equal to 28 minus 2L. We divide both sides by 2, and the W is equal to 14 minus length. Perfect. Now we have it in one variable so that when we go to our area statement and we're trying to maximize the area, I can go area is equal to length times the 14 minus L that's W. And now I can get this as area equals 14L minus L squared. Perfect. Now here's where we take the derivative. So I can write this as dA over dL, which is also equal to, we can write this as A prime of L, and that would be equal to 14 minus 2L. Now we set this to 0. 0 is equal to this 14 minus 2L, and if we isolate for L, we're going to get that this is 14 divided by 2, which gives us 7, and the units of this are centimeters. So we get that the length is going to be 7 centimeters from here, and I'm just going to highlight that. Now, this is also the critical number. Because it's where the derivative is equal to 0 or it's undefined, we're going to use this as our critical number. Now, in step number 5, I'm going to go up here and I'm going to build up my table. So I'm going to go step number 5. I'm going to write out just that short table we've done before where I have my 2 columns. Because I only have my one critical number, it goes here. And I'm going to use 1 and 8, just like the last problem. And test point right here, I'm going to write my A prime of L and A of L, meaning what happens to the derivative, what happens to the function. Now from here, if I sub in 1 to this derivative, it's 14 minus 2. 14 minus 2 is going to be a positive. 14 minus 16 is negative, so it's going to be increasing on the left-hand side and decreasing on the right, and we would identify that as a maximum, which is exactly what we're looking for. We're trying to figure out the maximum area. So at this critical number, we get a maximum. So now in step 6, we're going to put this all together. If we know that the length is equal to 7 centimeters, then the width is equal to 14 minus 2 lengths. So width is equal to 14 minus 2 times the 7, which ends up giving us that we have, because I'm looking at the wrong definition of this. It's 14 minus L. That's our definition for W. I was going to say this is going to give us 0. So I'm just going to erase the 2 and just put the length there. So length and length. And therefore that length is going to be 7. So the width is going to be also equal to 7 centimeters. Okay, that's kind of a coincidence. So not only is the length 7, but the width is 7, which we just found. Now we want to figure out the area and then put this in a sentence. Area is equal to length times width, which is equal to 7 times 7, which is equal to 49 and centimeters squared. We're going to put our units, we're going to highlight it. Now we just need our sentence. Therefore, the maximum area is 49 centimeters squared when the length and width are both 7 centimeters. Just a nice, clear, concise sentence that indicates that this is our final solution of a maximum for this situation. Now, it's kind of a little bit strange that in both these problems, we've got the same value for both of the things we've solved for, but that's okay. You can have the same length and width or the same numbers or whatever else it is. That's not totally wrong. So we look at this and say, that's fine, just pure coincidence that we get the same values. All right, let's continue to our example 3. So these are going to step up and get a little bit harder each time, but we're going to try and be very clear with where we go with these things. So in this example, an open top box with a square base is to be constructed with this amount of material. Now, when they describe it as this amount of material, what they're describing is the surface area. So if you just wanted to put below here that that's surface area. So we're going to definitely start with the surface area equation to get things in one variable and then solve. What is the largest possible volume? That's just a fancy way of saying what is the maximum volume. So right away, we want to define our variables. In number 1, let L, W, and H be the length, the width, and as you could imagine, be the height. Perfect. What is the restriction on both? All of these, I should say. L, W, and H all must be greater than 0, or else this wouldn't be a three-dimensional shape. Now, from here, we're going to use our perimeter equation to establish this in one variable. So what I'm going to do is I'm going to go the surface area, or what I'm just going to use as A, is equal to, well, because it's an open top box, for the base of this, it's going to be L times L, because that's going to represent the square base, plus 4 times the length times width, which is the 4 sides that surround it, which actually what I should be using here. And actually, no, that's okay. I can use the width of this thing. I don't actually need, so because the length and width are actually the same, I'm going to use L for both of them because it's a square base. And then for the height, I'm just going to use W, but you could use H. Actually, let's use H. I kind of go back and forwards on this. It really doesn't matter, but I'm going to use H here. So let's just make a couple edits here. Because it's a square base, again, it's going to be L times L, or just L for both the length and width. And then the height is going to be the distinct factor where both the L and the H need to be greater than 0. Perfect. So surface area is the square base, which is L times L, plus the 4 sides, which are the length times height. Okay, we want to solve this for H such that we can get an isolated variable. So 2,700 centimeters squared is equal to length squared plus 4L times H. I'm going to rewrite this as our 4LH is equal to, and then I'm going to have the 2,700 on the other side minus L squared. And then I'm going to divide both sides by the 4L, and this is going to give me 2,700 minus L squared all over 4L. Perfect. So now we have an H in terms of L, which then when we go to our volume statement, we can put this together quite nicely. So for step number 3, we know volume of a box is equal to the area of the base times the height. And the area of the base in this situation is L squared times H. But instead of writing it as L squared times H, I'm going to put L squared times 2,700 minus L squared all over 4L. I'm going to cancel off an L from each of these. So L and L squared. This is going to become 1L in the top. Now I'm going to get that the volume is equal to, I'm going to just pull out the 1/4 and then write the interior as 2,700L minus the L cubed. Perfect. So I distribute this L into the brackets, and then because this 1/4 or this numerical coefficient can technically be removed out to the front, I'm going to do that here. Okay, now when we take the derivative, this is going to allow us to do to solve for our critical numbers. So bringing this up above, because I can do this by the power rule, and I can just leave that 1/4 out front, I'm going to go dV over dl, because it's in terms of L, which is equal to V prime L, is equal to, and not T, but V prime L. I'm going to take the derivative of this 1/4 2,700 L minus L cubed. That's going to leave us with 1/4 bracket. This is going to become 2,700, and then minus the 3L squared from the L cubed. Perfect. Okay, now from here, we set our derivative to 0. So I'm going to go V prime of L is equal to 0, which is 1/4 in the bracket 2,700 minus 3L squared. If I multiply by 4, the other side is just going to become 0. So it's 0 equals 2,700 minus 3L squared. I bring the 3L squared to the other side, which is equal to 2700. I divide both sides by the 3, giving me L squared equals 900, and therefore I get length equals plus or minus 30. Now, for those of you that see the minus, you're like, we can't have a minus, so we're going to cancel that out, and we're going to write extraneous. You could also write these side by side and just go plus minus and then cross it out, but I'm just going to cancel out the negative and write ext, meaning the extraneous one. So length is equal to 30, and the units are going to be in centimeters. So I'm even going to include that. Great. Now we want to do our test point here so that we can test this, because again, this is where our critical number is located at. Your critical number, and just to include the theory alongside this, maybe I'll just do this off on kind of like a curly bracket here. If I take this, critical numbers are at when the derivative, and I'm just going to call it f prime of x, is equal to 0, but depending on what function you're dealing with, it might be v prime, it might be, t prime, or whatever else your variables are. Whatever that first derivative, it's your critical numbers are located at the derivative being 0 or undefined, but mainly where it's 0. Okay, great. Now let's put this together in the table. This is going to be for step number 5. I'm going to scroll down here and be like, well, in step number 5, we put together our short table that we've done before. We put together our 2 column lines, and we put together our 30 here. And I'm just going to use simple numbers, 1 and 31 for the test points. And my derivative is going to be v prime of L and v of L. Great. Now, we want to plug it into that first derivative. So if I plug in 1 to this first derivative, I'm going to end up getting a positive number. So I'm going to go down to that table, and I'm going to put a plus in here. If I put in 31 into that same function right here, I'm going to end up getting a negative. So my v prime becomes negative, and therefore the function on that interval is increasing on the left and decreasing on the right of the critical number. So at the very bottom of this, what we would do is we'd put a dot and we'd write maximum, which in this given problem, that's what we're looking for. What is the largest possible volume? The largest possible volume is designated when our value for the length is going to be 30. So now we got to figure out the other values. I'm going to say if the length is equal to 30 centimeters when it's maximized, then our height is going to be equal to, and we're going to plug it into that height formula we derived earlier. It's 2,700 times the 30 minus the 30 squared, which is L squared, divided by the, and I just want to make sure I got this right. Yeah, divided by the 4 times 30. Great. So the height from here, I think we might have enough room here. The height is going to be equal to, when we do this, we get 15 centimeters. When we simplify that, now to determine the volume, volume is equal to L squared times the height. Therefore, volume is equal to 30 squared times 15, which is equal to, we end up getting 13,500 centimeters squared. And now you want to put it in a sentence. Therefore, the maximum volume is 13,500 centimeters squared when the length is 30 centimeters and the height is 15 centimeters. Not to have that, get really condensed at the bottom. That's kind of just a product of doing the sentence fairly quickly, but making sure to have all our details in there. And with this one here, all they asked us actually was what is the largest possible volume. So we don't technically need to include the length and the height, but because we solve for them and they're part of getting the solution, I like to just sometimes throw them in there just to make sure that we're being as specific as possible to the problem. Okay, now again, we're kind of advancing into different types of problems. So this is another one you might see, and it's on the assignment actually, one very similar to this. And it's talking about this idea of saying, can we take points and place them on a curve and then also have them connected to some sort of shape or some sort of situation, like connected to a parabola making a shape or whatever it might be. And we want to figure out either the closest points to some sort of curve from another point, or we want to figure out how do we maximize a shape that's inscribed. It's kind of topics like that. So in this problem, we're finding points on a curve of y equals x squared that are closest to 0 and 3. Now, to draw this out right away, it's very important to have the visual. I'm going to just draw my x squared graph. So I'm going to draw this one in blue, and it's going to go through 0, 0, and extend this way. And then on top of this, I'm going to make sure to plot in my point, which is at 0 and 3. It's the y-intercept. And I'm just going to make sure that's just a little neater. So 0 and 3. And we want to figure out if I put points on this graph and they're the closest possible points to that, then where would these points be located? So basically, what is that closest point? Now, from here, I'm going to connect this with a line here. I'm going to connect this with a line because technically we're trying to figure out what is that distance between the y-intercept and whatever point is over here, which I'm going to generalize as x and y, and whatever point is over here, which would be designated as negative x and y. Technically, they're symmetrical, right? Because it's a y-intercept, it's x squared. The closest point will actually be the closest point on the left and right-hand side of this graph. Now, something to note here is that your y is actually x and x squared, because from above, we see that this y is equal to x squared. So I'm just going to rewrite each point and write them as negative x and x squared, just so that we can use these later on. Now, off to the side of this, what I really want you realizing is that we've actually generated a right angle triangle where we can use Pythag to figure out what is this distance so that we can get the minimum distance here. Let's do that off to the side. We're going to sketch out one of these triangles. I'm going to go down by some amount, I'm going to go over by some amount, and then I'm going to connect those with a line here, and I'm going to call that the distance right here. Perfect. And then my vertical distance is from the y-intercept down by y units, from the x-axis or from the 0, 0 origin point over by some x value. So we go down by some amount of units and over by x in order to get to our point that's on the parabola. Perfect. Now let's use this together here. I'm just going to annotate just a little bit more. Right at the very top, this is going to be our 0 and 3. At the bottom, this is our x and y from our visual on the left-hand side. Okay, we want to minimize that distance represented by d. So in our equation, the equation that we're going to build out here is actually just based on Pythag. D squared is equal to, we're going to take our x squared and then plus the 3 minus y squared. So from our triangle here, in order to get that distance squared, we're going to go the one side length squared plus the other. Now, instead of writing this as y, what I'm going to do is automatically just transform this into terms of x. So it's going to be plus 3 minus, well, y in this problem is x squared, all squared. Now from here, we're going to expand this out. So d squared is equal to x squared plus, remember, we write this out twice. So 3x squared minus 3x squared, like this, or I should say multiplied by the 3 minus x squared. Now when I expand this out, it's going to give me distance squared, which is equal to x squared plus, and I'm going to do the combination just in my head here. 3 times 3 is 9. Then we're going to have negative 3 and negative 3x squared, which is negative 6x squared. And then we're going to get plus the x to the power of 4. There we go. Now I'm going to simplify this as d squared equals, we have x to the power of 4, x squared minus 6x squared gives me negative 5x squared, and then plus 9. Excellent. Now what we want to do is we want to square root both sides so that we get distance, which is equal to the square root of x to the power of 4 minus 5x squared plus 9. Excellent. So this would be the distance that represents from that 0 and 3 to whatever this x and y is. Now, we're going to take the first derivative of this. So for step number 2, I go over here and I'm going to write this as d over dx of the distance, which is equal to, on the other side, if we know that the square root is raised to the half, then this is actually chain rule. We're going to drop the half, keep the x to the power of 4 minus 5x squared plus 9 on the inside, subtract the 1 from the exponent, and then multiply by the inside derivative, which is 4x to the power of 3 minus 10x. Okay, great. Now moving this in terms of positive exponents, I'm going to write this as the distance derivative in terms of x is equal to, we have our 4x to the power of, and actually I'm going to take a GCF out of this. Right away, if I realize that these both divide by 2 and they divide by x, I'm going to put the 2x out front, leaving behind 2x squared minus the 5 on the interior, and then divided by 2 to the square root of x4 minus 5x squared plus 9. Great. Now, last step, just cancel out those 2's. 2 over 2, that's going to leave us with nothing there. Okay, To determine the critical numbers, we actually can determine them just purely based on this numerator of x times the 2x squared minus 5. This part in here, I'm not going to see any restrictions here. I think we're okay here, but our critical numbers can come from here in this numerator piece. So I'm going to set this and say, well, the critical numbers are at, and one of them is going to be x equals 0. The other one is x equals plus or minus the the plus minus square root of 5 over 2, where the plus minus square root 5 over 2 comes from here. If I isolate this for x, it's going to give me the plus or minus square root 5 over 2. Now we have three critical numbers here, one of them being the 0, and then the other two coming from this bracket. We want to make sure we place them on our first derivative test chart to see what's happening with the signs. So I'm just going to sketch out just a little bit larger of a table here. So we're going to have 1, 2, and 3. I'm going to put these all on there. So I'm going to put my negative square root 5 over 2. I'm going to put my positive square root 5 over 2, and then 0 in the middle. The test points that you can use are -2, -1, 1, and 2. And then again, I like to sometimes just write test point right here at the top left to indicate that that's what we're using. I'm going to write d prime of x, d of x. And so now we're going to do our sign analysis on that derivative. What I realize is that when I plug this in and I plug in the -2, the -1, 1, and 2, I'm going to get the following signs. So I plug in each of them to this derivative here, and I find that I get a negative, positive, negative, positive. And so from here, this is going to lead us to having the following. The graph decreases, increases, decreases, increases, and therefore we're going to put a dot here, here, and here. We're going to have a minimum, a maximum, and then again a minimum. And the reason I short form the maximum is just because I needed to fit all three of these. So you could just put min, max, min, but I like to sometimes write them fully out. Great. Now, to determine the distance that maximizes this, all we're going to do is just plug in we're going to plug in that overall x value, because we know that it's maximized at this root 5 over 2. And if it's maximized at this root 5 over 2, then we should be able to figure out the coordinate of the closest point. So, because we want to figure out the points that are closest, to do that, and I just want to keep track of my steps here. For step number 3, we're going to go the distance is minimized at the points, and I'm going to do the live calculations within my answer here. So at the points, we're going to do f the square root of 5 over 2, and we're going to do f of the negative square root of 5 over 2. Well, because both of these are going into x squared, it's going to be root 5 over 2 all squared, which is equal to 5 over 2. And then the other point is going to be at negative the square root of 5 over 2 all squared, which is also equal to 5 over 2. And therefore, the points are going to be located at the square root of 5 over 2 and 5 over 2, and the negative square root of 5 over 2 and 5 over 2. Perfect. So I'm just going to include the sentence with my answer, the points that make up the answer, and therefore that's our summarized piece here. Now, again, you could write even more detail on this. You could say the distance is minimized between the y-intercept and the curve at these points. Whatever you want to do to make this as specific as you can, but I would just recommend including as much detail as you can in your sentence. Okay, now moving on to our next one. Again, as you're going to notice, we have a full page to work with. That's because each of these are going to step up in terms of the amount of work required and just kind of the detail to be looking for. So for this one, find the dimensions of the largest possible rectangle that can be inscribed, meaning inserted within a circle with a radius of 4. So what I'm going to do right away is I'm just going to draw out a visual so we can kind of see what's going on. And then I'm going to draw in our largest rectangle that might exist. So it's going to go like this, 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 and this. There we go. Now, what I'm going to get us to do here is I want you to write in that this is the length, this is the width, and then I want you to write in the cross section that goes across the circle, where this part here from the center to this piece is going to be our 4 centimeter radius right there. And then we know that the length across, therefore, is going to be 8 centimeters, which is the circumference of the circle. Not the circumference, but the diameter of the circle. Okay, great. So the hypotenuse of this rectangle is technically 8 centimeters, the hypotenuse, which is the cross section. We have a length and a width. Now, to determine this largest possible rectangle, I like to sometimes highlight that to make sure we're good. In step number 1, outside of doing our visual, we want to define the variables. So let L and W be the length and width. Perfect. And we're going to define both L and W greater than 0 because we don't want to have either one be less. Now, we're going to use Pythag in order to figure out this in terms of one variable. So for step number 2, I'm going to go 8 squared, which is the cross-sectional diameter, is equal to the W squared plus L squared. Now, we could technically isolate for either one, but let's say I isolate for W. I'm going to go, or isolate for L. It's going to be L squared equals 8 squared minus W squared. That means when we take the square root, it's going to be L is equal to the square root of 64 minus W squared. Now, this is going to introduce a restriction that's very important for us. So one of those restrictions is going to be the following. We're going to just do this off to the side. It's going to be very, very important we note this here. When we take this radical, it's 64 minus W squared must be strictly greater than 0. And the reason is because if this W value matches 64 and it becomes 0, then the length isn't going to exist anymore. So we're going to isolate this for W squared. W squared is less than 64, which means that W must be between -8 and +8. But clearly we see this as a faulty piece. It's not going to be between those two. It's actually going to be between 0 and 8. So we're going to make sure that we put this between 0 and 8, meaning W is an element of 0 to 8. Now again, the reason it cannot be 8 specifically is if I substitute 8 squared, this becomes 0 and the length would be 0. So if we get a critical number of 8, it's not going to be in the domain, so we got to watch for that. Same thing for 0. We wouldn't want to have a W of 0. Okay, great. Now that we've altered what our W can be and we've figured out what it can possibly represent, what I'm going to do is I'm going to figure out my area for this rectangle. We know that in step number 3 here, if I take the area, it's equal to length times width. Now we can place it in one variable. A is equal to, well, W equals the square root of 64 minus W squared times the W that is on the outside. That means the area is equal to that statement, which involves product rule. So when we go to step number 4, and we're differentiating this, dA over dW is equal to A prime of W, if you wanted to write it that way, which is equal to, by product rule, we're going to take the differentiation of the F. So this is going to be of the square root of 64 minus W squared multiplied by W plus the square root of 64 minus W squared d over dW of W itself. Perfect. When we derive this, first one is chain rule. So we drop the 1/2, we keep the 64 minus W squared, we subtract the 1 from the exponent, and then we multiply by the inside derivative. But there's also that W that's on the outside. Plus, we take the square root of 64 minus W squared, and then we multiply by 1, which is the derivative of W. Now, I'm actually going to make this into the 1/2, and the reason is so that we can remove a GCF. So instead of writing it like this, why don't we write it as 64 minus W squared to the 1/2. I'm going to write it in that manner. Okay, perfect. Now we're going to pull out any terms we can. Clearly, we see a 2 and divided by 2. Let's just eliminate those. When I remove a GCF, all I can remove is the 64 minus W squared to the 1/2. So I'm going to go 64 minus W squared to the -1/2, which inside is going to leave me with, we're going to take this and be like, well, that's W squared because I took off this piece and I'm only leaving the W's that are behind, so W squared. And then off the other one, if I take off a half, but it's a -1/2, it becomes a half minus a half, which just leaves us with the 1. So this is going to be 64 minus W squared to the 1. And I'm going to close my bracket. Perfect. Now, from here, I just want to keep track of the signs actually, because I feel like there's a negative I'm missing. That's it. Right here, we have a negative that is on this term right here. The W times W includes this negative right here. So in the notes, please put a negative in front of that W. Great. Okay, from here, I'm going to write this in terms of, in the numerator, I'm going to have negative 2w squared plus 64, and then in this denominator, the square root of 64 minus w squared, where this part became the numerator, and then this outside piece drops down to the denominator as the root of a half. Now, let's take out a negative 2 in the numerator, leaving me with w squared minus 32, and then in the denominator, this square root of 64 minus w squared. Okay, critical numbers are located at, well, right away, I have critical numbers at the following points. Critical numbers at, from our numerator term, w squared minus 32, that's going to make w is equal to the square root of 32, which is equal to the 4 root 2 centimeters. And the reason I'm not doing plus or minus for this is because we're not going to have a negative width, so I'm going to make sure I just put in the positive version. If I look at the denominator, well, I see that this is going to be 64 minus w squared, which is greater than 0 by that restriction. And since it has to be greater than 0 because we don't want to have a 0 denominator, it actually means that it has to be, equal to 8 or less than 8. But theoretically, it can't be 8. So I'm not going to worry about that denominator because we've already established that the length of this and the width both have to be between this 0 and 8, or else it breaks apart. Okay, good. So here's our critical number. We have one critical number. Let's make sure we go to our step number 5, which is putting this in the table. So I'm going to build out my basic table like so. I'm going to put my 1 column line, and then I'm going to put the 4 root 2 right here. The values I'm going to test with are both at 4 for the left and 6 for the right, and I'm going to go test point like this. I'm going to put in my area derivative with respect to w and my area equation with respect to w. And from here, I'm going to figure out that the signs of these, if I was to plug in 4 into the derivative calculation, which is right here, this is going to give me a negative on the, or actually it's going to give me a positive on that side. So I'm going to get a positive for 4. And then if I plug in 6 to here, I'm going to end up getting that this is a negative. So we see that it's increasing on the left, decreasing on the right, and this must be a maximum at this point. So I'm going to write that clearly in. There is a maximum when the width is equal to 4 root 2 centimeters. Okay, now what you could do, and this is going to be important, and I might actually just represent it one time because some of you like smaller tables, but I actually prefer like bigger tables if possible. So the table that I would typically write in class would be something more like this one, where I'm going to put the 4 root 2 right here. I'm going to put my 4 here. I'm going to put my 6 here, the test point here, and then I'm going to break apart the function, the derivative function, into all its components. So negative 2, w squared minus 32, square root of 64 minus w squared. Then I'm going to write my a prime of w and my a of w. So I break it into the components so that it's really easy to test. Negative and negative, because negative 2 will stay negative. W squared, 4 squared, which is 16 minus 32, that's negative. 6 squared is 36 minus 32 is positive. And then if I do 64 minus 16, this is positive. 64 minus 36 is also positive. So on this interval, I'm going to get a positive to negative, meaning it's going to be increasing to decreasing, and we also get the maximum. So if you're really struggling to enter these into your calculator and you're like, oh my goodness, like this is mentally taxing to put it into a bunch of components and then simplify all at once. If you don't want to do it all at once, take each of the components and then put them in their own test category. So one part, the next part, the next part, and then you can deal with all their signs at once. I may suggest that for some of you. Okay, now as we go down below to step number 6, our end goal is to figure out, we want to figure out the maximum possible rectangle, or the largest possible rectangle, specifically the dimensions of that largest possible rectangle. So from here, we may solve for the area as well, but based on the context of the problem, we just want to figure out the dimensions of the largest possible. So I'm going to solve this, and I'm going to go step number 6 below. We are going to say, well, if we know if w is equal to 4 root 2, and this is centimeters, then, and we're going to solve for the rest of them, our length was given by the square root of 64 minus the w, which is equal to the square root of 64 minus, and this is w squared, sorry, that's 4 root 2 all squared, which is equal to the square root of 64 minus, this is 16 times 2, which is going to be equal to 32, meaning this becomes the square root of 32, which is equal to 4 root 2. So therefore, the length is also equal to 4 root 2. Oh my goodness, these lesson notes are full of lengths and widths that are the same. So our width is here, our length is here, and now we can figure out the area and then just summarize it. Area equals length times width. Area is therefore equal to this 4 root 2, but instead of writing out twice, I'm just going to square it. So therefore it becomes 16 times 2, which is equal to 32 centimeters squared. Perfect. I'm going to highlight this. Now it's time for the sentence. The area is maximized with a length and width of 4 root 2 centimeters. And you can just even simply put the area is, and you can just write in the number with the units. Not that it asked for that, because the context only asked for the dimensions that maximize the area, but I sometimes will just solve for it just because why not? Okay, great. So you're seeing how these problems can get quite expansive, right? And you have to be very careful with your definitions of where are the limitations on the lengths and widths? How do we define our variables? Can we make sure we're using the two equations to get things in one variable? And then please make sure you have your first derivative test somewhere in your problem, or else you're going to lose marks. That's a very important piece to have. Okay, going down to example 6. Example 6 is again another one where we want to be very careful with the details here. So we have a window that's in the shape of a rectangle and it's surmounted by a semicircle. Now surmounted just means topped by a semicircle, and they say the diameter is the length of the rectangle. Now right away what I'm going to do is just draw a quick visual here. So I draw out my rectangle, which represents the first part, and then I draw out my semicircle that is surmounted on the top. Now, what they told us is that the diameter is the length. So we're going to write length and width, where this is also the length right here. And I'm just going to backpedal that and put it a little neater. There you go. Okay, they've given us the perimeter and they want to determine the maximum area. Now, again, as soon as they give you the perimeter, you know that the perimeter is where we're going to start in terms of getting everything into one variable. So I'm going to just at the very top start with defining the variables. Let L and W be the length and width. And I'm going to write L and W are greater than 0. Perfect. Now we're going to discuss our perimeter. So step number 2, the perimeter is equal to, we have 2 W's plus 1 length plus half a circle, which is half 2 pi r. Because we know 2 pi r is going to represent the perimeter of a full circle. So if we only want half of it to get the half surmounted part of the circle, it's a half of the circumference of a circle. The 2w is 1w and the second w, and then the 1 length comes from the bottom here. Now they also describe it in terms of, if we know that this is the length, then the radius, which you may want to write in here, the radius is just half of that length. So the radius of that surmounted circle is 1/2 L. So instead of writing this as R, I'm going to write this as 1/2 L. Because again, the radius is 1/2 the length of this. So I'll just put a little scribble in there. Perfect. Now, the perimeter, which is 18, is equal to 2W plus the length plus 1/2 2 pi, and then this is 1/2 L. Well, we can either cancel the 2 and 2 in the front here, or the 2 and the 1/2 from the other piece, but I'm going to cancel it off the front. This is going to be 18 is equal to 2W plus length plus 1/2 pi L. Now, we want to make sure this is in one variable, so I'm going to isolate for the W. 2W is equal to 18 minus L minus 1/2 pi L. I divide everything by 2, and I get that the W is 18 divided by 2, which is 9, minus 1/2 L, minus 1/4, because we're dividing that by a half, and then pi L. Great. We used our perimeter to solve for this in one variable. Now, that one variable can then be substituted in for our area statement so that that can be in terms of one variable when we differentiate. So for step number 3 below this, we know that area of this is going to be represented by, we're going to take our length times width, which is the area of the rectangular window, plus 1/2 the area of a circle, where the area of a circle is pi r squared, but because we have a half circle, it's surmounted by the half circle, it's got to be half a circle's area. Okay, again, we're going to use that same derivative here, or the same substitution where the radius is 1/2 L, or 1/2 the length. So now when I do my area, which I'll do below here, area equals L times W plus 1/2 pi, instead of R, this is going to be 1/2 L all squared. Now, from here, I'm going to make sure I sub in not only the 1/2 L squared, but I'm also going to sub in the W. So this is L times 9 minus 1/2 L minus 1/4 pi L, plus the 1/2 times, this is going to become 1/4 L squared. And so I'm going to make this 1/8, and this is going to be pi L squared. Now, continuing this out, I'm going to write this as 9L minus 1/2 L squared minus the 1/4 pi L squared plus 1/8 pi L squared. Now, we see that we can combine these pi L squared, so I'm going to do that right before I take the derivative to get our critical numbers. So this is going to be 9L minus 1/2 L squared. 1/8 plus 1/4 is going to give us negative 1/4 pi L squared. Great. So now I have this all in terms of my, I have this all in terms of a nice combination here. Perfect. Now, from here, I'm going to get that when we take our derivative from this, let's make sure we move on to our next step, which is going to be the dA. So step number 4 is going to be our dA over dL, or we could write this as A prime of L is equal to 9
You'll need to continue on your iPhone.
So we can continue and make this 9, and then this is going to be, we drop the 2, it's going to become just the 2 divided by 2, which is negative L. And then if we drop the 2 here, it's going to become negative 1/2 pi to the L. There we go. Now, I just want to double check here with our solution. We have a plus, a minus. What I might actually do here is just to make sure that the derivative is all correct and we're not missing any sort of combinations here, I'm just going to backpedal it to this area piece here. And I'm going to do my derivative from this step here, just to make sure we get everything appropriately, because I don't want to make any combinations that might throw this off. So from here, this is where I'll do my step number 4 for this. I'm going to go step number 4, dA over the dL is equal to A prime of L, which is equal to 9 minus, this is going to become L, minus 2 over 4, which is 1/2 pi L, and then this one's going to be plus 1/4 pi L. Great. Now I can combine my pi L's here. So this is going to become A prime of L is equal to 9 minus L minus the 1/4 pi L, just to make sure that we're good there. Awesome. Now I can take this, and to find my critical numbers, we know that critical numbers are at where the A prime of L, or the first derivative, is equal to 0. So I'm going to go 0 equals 9 minus L minus 1/4 pi L. I'm going to solve this for L by going 9 is equal to, we're going to move the other two components to the other side. So the 1/4 pi L. And then I'm going to factor out the L. So this is L, 1 plus 1/4 pi. And we're going to divide both sides by the 1 plus 1/4 pi, which gives us a length of 9 over 1 plus 1/4 pi, which I'm going to just take this and put it into a decimal form. It's 5.04089 continued on. There we go. So we have this, and then in terms of the units, this is going to be in meters. Now, I know this was not super pretty. If I'm looking back at this, I'm like, oh my goodness, this is a lot going on. We got a perimeter putting in terms of W, we got an R substitution, we have to do this derivative quite neatly, and then we have to get a decimal, but that's all fine. So this is going to be our critical number that is given from here. Now, we're going to put this in terms of a chart, so I'm going to go for my step number 5, which is down below here. Let's put this into just a small chart. we're going to have our 2 rows by roughly our 2 columns here. 3 columns, I guess, if you count the first one. Our number is going to be 5.04 ... I'm just going to put dots. We're going to put maybe 4 on this side and 6 on the other as our 2 test points. And I'm going to go A prime of L as my first column, and then A of just L, no prime on the bottom one. Now, where we're plugging this into is we're taking the 4 and 6 and we're plugging them into this here. So it's 9 minus 4 minus 1/4 pi 4. In the first part, this is going to give me a positive, and then it's going to give me a negative, meaning your function is increasing, then decreasing around this critical number. So now I'm going to plug in right at the very bottom here. If we know it increases to decrease, this leaves us with a maximum. Excellent. Okay, now our question asked us, if the perimeter is 18, then determine the maximum area to the nearest tenth. We do not need to figure out the length and width of this, although I will do that because I think it's important for this problem just to have length and width in the area. If you just solve for area at this point, that's probably more than enough. But in our equation in terms of the area, we needed that W technically. I guess if you just plugged it into the one where we subbed an L, I guess you could do that. But I'm going to solve for my W so that I can make this easier. So right at the very bottom here, I'm going to solve for this and go in step number 6. If the length is equal to 5.04 ... and this is meters, then the width was equal to, based on our definition above, it was the 9 minus 1/2 times the length, which is 5.04 ... So I'm going to take that stored value and then minus the 1/4, and this is going to be pi times the length, which is 5.04 ... So we get a W equal to roughly about 2.52, and this is in meters. So now I have a length, I have a width, and I want to figure out the area of this because that was the whole goal, determine the maximum area. So I'm going to plug it into, if you looked above, our area equation was this one, which is not pretty at all. We're going to sub in our length and width to this. Or we can even sub it honestly into this original statement here, which was this one right here. That's going to be probably our easiest one because we don't want to be subbing in where we have just lengths and it's this big statement. If we can make it a little smaller, we're going to do that. So I'm going to plug it into that one below and then give a sentence here. So I'll arrow up. Whoops, don't want that to be there. I'm going to just arrow up and then go area is equal to, and we're going to plug it into the 1/2 pi, the length, which was this 5.048. So 5.048, or 408, that is, all squared, and then plus the 5.0408 bracket times the width, which was 2.52. And then this was the 1/2 times pi times the radius squared plus, so this is the area of the circle, this is the area of the rectangle. When you put them two together, you're going to get that the area is equal to, when rounded to the nearest tenth, because that's what the question wanted, it's 22.7 meters. So therefore, the area is maximized with a value of 22.7 meters squared when the length, whoops, I'm going to make sure that's a little neater, length is 5.0 meters and the width is the 2.5 meters. Great, there we go. We're going to highlight this and good. And again, all it asked for was the maximum value for the area, but again, I like to sometimes put them both there. All right, now going to our next problem here, example number 7. What is the maximum perimeter of a right triangle with a hypotenuse of 20? Well, for this example, what we got to be thinking is it's basically just Pythag using the hypotenuse and then doing a derivative on that and testing to see what those x and y values become from there. So what is the maximum perimeter with this right triangle? I'm just going to draw out the visual of this. So it's going to look like the following. We have this triangle. We know that the hypotenuse is going to be 20 and it's in centimeters. So I'm going to include those units. I'm going to put X and Y right here. Now, right away, I just want to define let X and Y be the two sides where X and Y are both greater than 0, or else this wouldn't be a triangle. Now we're going to set this up for a Pythagorean situation. 20 squared is equal to X squared plus Y squared. Well, from here, I'm going to then isolate this for Y. So I'm going to go Y squared is equal to 20 squared minus X squared. I take the square root of both sides. I get Y is the square root of 20 squared, which is 400 minus X squared. Now this is in one variable. So when I do my perimeter statement, the overall perimeter of this is going to be equal to the 20, which is the hypotenuse, plus the X, plus the Y value, which means that the perimeter is going to be equal to 20 plus X plus the square root of 400 minus X squared. Now, to figure out the critical numbers, remember, we're going to have to do our derivative. So for step number 4 here, I'm going to go dp over dx, or what I could write as p prime of x is equal to, derivative of 20 is 0, derivative of x is 1, derivative of the square root of anything is going to be 1/2, bracket, by chain rule, keep the inside, subtract 1 from the exponent, and then multiply by the derivative of the inside. Now, just as we've seen in the past problems, sometimes you can actually cancel out the 1/2 and the 2 if the inside derivative is 2. Now from here, this is going to simplify as a derivative of p prime of x is equal to 1. We're going to get plus the x divided by, and this is actually a negative x, so I'm going to make that negative x over the square root of 400 minus x squared. To make this one fraction, I'm going to write it as p prime of x is equal to the square root of 400 minus x squared minus x all over that square root of 400 minus x squared, because we multiply it to the numerator and denominator. Now, to get the critical numbers, remember, critical numbers at when the p prime of x is either undefined or equal to 0. So I'm going to set the overall function to 0. We see that in the denominator here, as long as the x is not 20, then we're good. So we're going to see this as a significant number at that point, which I'm actually going to write just kind of off to the right. If I take 400 minus x squared, and it must be greater than 0, then x squared is less than 400, then it must be that it is between 20 and negative 20. But as we know, that can't be the reality because the x value has to be greater than 0. So as long as x is less than 20 and greater than 0, it's satisfied. The significant number out of this is actually at 20. We have a significant number or an endpoint at x equals 20. That's as high as it could go, but we don't want to touch that or else it's outside the domain. So now we go to our critical numbers and we go, well, if 0 is equal to the p prime, then we're going to take the square root of 400 minus x squared minus the x squared on the outside, or just minus x, sorry. I'm going to move the x to the other side, which is equal to the square root of 400 minus x squared. We square both sides, giving me x squared equals 400 minus x squared. This gives me 2x squared equals 400. And if I divide by 2 and take the square root, I get that this is going to be equal to the plus or minus square root of 200. But we only want the positive version, so we're going to take this and say, well, it's equal to positive 20, and this is going to be in terms of, no, not positive 20, what am I doing? If I take this, this is going to be 10 root 2, because I can break it into 100 times 2, take out the square root of 100, which is 10, and therefore this is my value. Perfect. Again, we only want the positive value, and the reason we only want the positive is because the negative is not going to be considered in terms of a length and width. All right, great. So our critical number we're testing around is here. And what we're going to do is we're going to break apart this derivative into all its components. Just like we did before, if we break it into the components, sometimes it's easier to plug into. So I'm going to build out my table from here. So I'm going to try and use my straight lines here. Here's the, and draw out as many rows as you can just to give yourself all the space. We have the one critical number, which I'll put here, that critical number being 10 root 2. The numbers on the outside of this, let's say we use 1 and 19. Because again, this is going to start at 0 and end at 20. It can't go higher than 20, but it can't go lower than 0. Now the test point part, I'm going to put right here. And then I'm just going to break apart the derivative. In the numerator, it was the square root of 400 minus x squared minus x. In the denominator, it was the square root of 400 minus x squared. And then we're going to take what happens to the overall derivative, what happens to the overall function. Now, if I plug in 1 to that first bracket is actually just going to give me a positive, so I'm going to get plus. If I plug in the 19 to that, I'm going to get a negative. If I plug in 1 to this next one, it's positive. I get a negative for my second one, or I should say I get a positive for it. My bad. So that's going to be a plus. And then overall, the derivative is going to be positive. This derivative is going to be negative. So it's increasing to the left, decreasing to the right. And therefore, I can say that at this critical number, we have a maximum. So at this value for x, we're going to get a maximum perimeter. Now, our problem asked us, what is that maximum perimeter? So I'm going to solve for x, y, and then add them all together with the hypotenuse. So just keeping track of my step numbers here, this is number 5. I'm going to go p of x has a maximum, aka the perimeter of x has a maximum when the x value is equal to 10 root 2 centimeters. The y value, which can be derived from, we actually had a statement above, which was the square root of 400 minus the x squared, which is 10 root 2, and this is squared, which is equal to, if I take this, it's the square root of 200, which is also equal to 10 root 2. Hey, look at that. We're getting the x and y that are the same thing again. And then, therefore, the perimeter is equal to the 20, which is the hypotenuse, plus 2 times this 10 root 2, because we have 2 of them. And if I realize that this becomes a perimeter, which is equal to 20 plus 20 root 2, I can factor out the 20 and write this as 20 bracket 1 plus root 2, and this is centimeters. So the perimeter is maximized with a value of 20 times 1 plus root 2 centimeters when the x and y are 10 root 2 centimeters. Perfect. There we go. And you can highlight this answer all together, basically indicating that we have all the values we need. And I'm going to make sure I highlight my perimeter, I'm going to highlight my x, and I'm going to highlight the y here just to make sure we have it all together. Great. Okay, last problem. We go on to example 8, which is about this Shaw Cable Company, so pretty well-known company around Canada. We are laying cable underground and underwater, and specifically they have different costs. So to lay wire underwater, meaning somewhere under this cross, because we want to go from this station to this station, and we want to do it in the most cost-effective way, aka the least expensive way to do this. So I'm just going to make sure I highlight this right here, the least expensive way to lay this cable, where it costs us $80 to go under the water, and then it costs us $40 to go on land. So clearly, we wouldn't want to go directly this way and then directly this way, because then we would be using a lot of material both ways. So what we're going to try to do, and we wouldn't want to go directly under the water either, that'd be very expensive. So what we're going to end up doing is the following. We want to go a little bit underwater, and then we want to go a little bit on land. That would be the ultimate end goal here. And I'm going to use arrows on the end just to indicate what the pathway is. Now, that means that from this, rather than going from P to Q directly, we're going to go, instead of P to A and then A over, where this is A and this is B, I'm going to label this distance right here as X between those two. So whatever distance we're going in terms of right from that point, that's what we're going to do. Now, from here, I'm going to take this and go, well, we know it's 100 up and it's X over. So to get the cable, which I'm going to call cable 1, in order to get the cable 1 across, and cable 2 is right here, cable 1 can be defined in the following way. Cable 1 equals the square root of 100 squared plus the X squared. Cable 2 can be defined by the 1200 minus the x distance we move over. Because whatever this is technically that wasted space on land that we're kind of moving away from that. We don't want to use this part on land. We're going to go underwater from here to here and then on land from B to Q. Okay, great. Now we have a definition in terms of how much cabling we're going to use, but we want to put this in terms of a cost statement here. So I'm going to write this in the following way now. For step number 1, we're going to say the overall cost of this project is equal to the cost of cable 1 plus the cost of cable 2. The overall cost is equal to, well, it's more expensive to lay the part underwater, which is 80 times however much cable we're going to use in terms of underwater. So this x squared plus 100 squared from our derivative or from our explanation above. And then I'm going to go plus the 40 multiplied by the 1200 minus x, which is our part that is on the land. So again, if you want to put this here, you can put up above. This is the part that is underwater. This is the part that is on land. And I know that's a little bit confusing when I use C1 and C2 in terms of cabling 1 and cable 2, because then when I go down below, I've added in the cost being multiplied to the quantity that is being used of each of these. Okay, perfect. Let's make sure that we do our derivative of this in step number 2 so that we can get our critical numbers. So in number 2, we're going to go dc over d of x is equal to c prime of x, the cost derivative. Remember that if we have these coefficients, we can save those till after. I'm going to do chain rule on the first, so I'm going to keep the 80 out front, and then I'm going to do chain rule on the inside, keep the x squared plus 100 squared, and then subtract 1 from the exponent, and then I'm going to multiply by the inside derivative, which is 2x. Okay, then I'm going to go plus 40 multiplied by the derivative of the other bracket, which is 1200 is 0, negative x is negative 1. Perfect. I'm going to close that off with a square bracket. Awesome. Now this is going to continue with, we can divide away the 2 and the 2. And so in my numerator, this is going to become 80x divided by the square root of x squared plus 100 squared. And then I'm going to have minus 40 from the other component here. Perfect. Okay, now in order to make this one fraction, just as we've done before, I'm going to write this as c prime of x is equal to 80 minus 40 times this square root of x squared plus 100 squared, and then all divided by the square root of x squared plus 100 squared. Now, what we should notice right away is that there's going to be no critical numbers exposed from this denominator, and the reason is because this will never be something that causes a restriction. There was no restriction on the domain in terms of nothing that would come from this denominator. This will always be positive here. So if this is always positive in the denominator, don't worry about it. Now we're going to define this and say our critical numbers are at when the c prime of x is equal to 0. That means I'm going to set my derivative to 0. And now I can use my numerator to help me solve for what these critical numbers are. I'm going to add the 40 square root of x squared plus 100 squared across is equal to 80. If I divide both sides by 40, I get the square root is x squared plus 100 squared, which is equal to 2. I square both sides, give me x squared plus this 100 squared is equal to 4. And then I have, just to make sure I have everything right, I'm noticing that there's something wrong in my derivative. Oh, it's this x here. Please include this x with the 80. So I need to have an x here, which means I need to have an x here, which means that I need to have an x here. And so this becomes 80x, which is 2x, which then makes this 4x squared. So please make that correction. There should be an 80x here, 80x here, an 80x here. When you divide the 80x by 40, you get 2x, which then if you square 2x, you get 4x squared. Awesome. Okay, now from here, this is going to give us where we have 100 squared, which is technically 10,000, which is equal to 3x squared. If you divide this to get your critical number, it's technically plus or minus the square root of 10,000 over 3. But from here, I can then say, well, the square root of 10,000 over 3, and I only want to use the positive one because our negative value is extraneous. We're not going to go a negative distance. So I'm going to then treat it as the square root of 10,000, which is 100, over square root of 3. If we rationalize this using the square root of 3, this is going to give us that we end up getting 100 square root of 3 all over 3. And in units, this is going to be in meters. Perfect. So this is how much technically, if I'm thinking about this as an x value, it's how much distance we want to go. Instead of going directly across, we want to go that amount over from that part. So what we're going to do is now we're going to get our absolute cost here. We're going to scroll down and go just based on steps. This is step number 3. I'm going to figure out what this cost is in terms of the least expensive cost. I do that by going C of the 100 square root of 3 over 3 into the function, which is going to be equal to 80 square root of the 100 square root of 3 over 3, all squared, plus 100 squared, and then plus the 40 times 1200 minus this 100 root 3 over 3, close the bracket. When I solve this, I'm going to end up getting that therefore the cost when the length away is 100 square root of 3 over 3 is equal to the nearest tenth, we're going to get 54,928.2, and this is the absolute minimum cost. So now, if we have this value, we're going to make sure we put it in a sentence with what this x means to us. So I'm going to do that up above here. I'm going to say, therefore, the least expensive way to lay the cable is when the cable is placed. And then because everything, I think they asked it in terms of the nearest tenth, I'm actually going to even round the 100 square root of 3 over 3. This could technically be equal to 57.7 meters. So I'm just going to put in the 57.7. It's placed 57.7 meters away from being directly across. Perfect. So it's that distance instead of just going directly across. I'm 57.7 meters just to the right of that. And the cost is we get this $54,928.2. There we go. Perfect. So to visualize this, I'm just going to go up to the visual and make sure I place on this 57.7 or this 100 root 3 over 3. It is this. So the least expensive way is to make this value for x equals 57. Whoops. It's going to be equal to 100 root 3 over 3, which is equal to, and I'm just going to drag this over just a tad, 57.7 meters away from A, which would be directly across. And as long as we take that path where it's 57.7 meters away from that going directly across, and then we continue on land, we'll get the least expensive way to do this. Perfect. Okay, that was a lot. That was tons of notes. I'm going to highly encourage you to practice. As you saw, these got a little more difficult, a little more difficult. The numbers weren't nice by the end, but you got to practice this. Optimization is a very difficult section, and if you're not practicing, it's going to be tricky. Now, to practice, we got 3 check your understandings that have the solutions posted on D12. So this is where I'm going to recommend you go next. All right, we'll see you in 4.4b.